Chapter 2 is all about the quantum mechanical model of the atom. And so in Chapter 1, we really talked about the atomic theory and what atoms are composed of and their arrangement. But now we're going to actually start to talk about what are those electrons doing. In the 1900s, scientists such as Einstein, Niels Bohr, de Broglie, Planck, Heisenberg, Schrödinger, and Dirac all started to study what happens when you get really, really small as far as matter goes. Really, really small things are called quantum, in the quantum world, or quantized. And this really helped to understand what matter, how it behaves when you get really, really tiny. So those tiny particles are electrons, protons, and neutrons. But the smallest of those, as we know, as far as mass goes, is electrons. And they have different behavior or properties than matter in the macroscopic world. Scientists started to notice that small matter started to act really strange. So these different subatomic particles could either exist in two different conditions. They could exist in the particulate behavior, right? So things that have mass and volume when you have certain conditions, but they also exhibited energy-like behavior as well, or kind of like we think of light waves when we have other types of conditions, and this is called wave-particle duality, where this duality is where matter can act as both a wave and a particle, not at the same time, but under certain conditions. So when we talk about atoms, a lot of the behavior of atoms is determined by the electron. And this is because electrons, if you remember, we have the protons and the neutrons in the core, in the nucleus, and then the electrons are on the outside. And so when atoms interact with each other, their electrons are interacting. So a lot of behavior of atoms is governed by electrons. The part of electrons that are governing much of the chemical and physical properties of matter is the light or energy form of the of electrons. And so when we talk about wave-particle duality, it's the wave part of electrons that are governing much of the properties. So quantum mechanics helps to explain trends on the periodic table, the way that elements bond, and the colors and sizes of atoms. It's also used to predict different properties due to the electron's behavior, so why certain elements are metals and others act like nonmetals, why some elements like to gain electrons or like to lose or gain more than one or lose more than one, and why some are very reactive, some elements are very reactive and some are inert or unreactive. So before we really dig into electrons, we have to talk about properties of waves or light. So light is a type of electromagnetic radiation. On light, we have two different oscillating waves, and they run perpendicular to each other. We have our electric field, which is in this case going up and down, and then we have our magnetic field, the blue line, running perpendicular and oscillating in a similar manner. And so the electric field is where electrically charged particles are experiencing force, and magnetic field is magnetized particles experience force in that field. And both of those waves are running and traveling at the speed of light. And that is 3.0 times 10 to the 8 meters per second. And it's governed by the letter C. And that is how fast electromagnetic radiation will travel when it's in a vacuum. So each wave has an amplitude. Now this is the height of the wave. So if we look over here on the right, we have a dim light source, which has a really small amplitude, and a bright light source, which has a very high amplitude. So brightness is really just differing on how high that wave is. So the larger the amplitude, the brighter the light. And then wavelength is the distance between waves. Wavelength is governed by or symbolized by the Greek letter lambda, which kind of looks like an upside down Y kind of, and it has units of meters, distance. So we can see here on our dim source, our distances between dim and bright are the same. This is the wavelength. So these two lights would have the same color. So this distance is related to the color of the light. And so we can see here on the top, this has a larger wavelength for red, and then yellow gets smaller, and then blue is even smaller. So the different colors just differ on how far apart those peaks or the troughs are. So the distance between the crests. And the wavelength, like I said, is related to the color. And this is intensive. It doesn't matter how much of the light I have, the color would still be the same. So once again, in this example here, the color is the same. I just have a brighter light down here and a more dim light down there. And then when we have white light, it's actually a mixture of all the colors. So if I have white light coming in here, then if you put it through a prism, prisms help to scatter the light, spread them out. We'll have red over here, orange, yellow, green, blue, indigo, and violet. So Roy G. Biv as we go down. And so here we have really small wavelength with the blue and indigo and violet, and really large or longer wavelengths up at the red. The next variable that we're going to talk about with waves is frequency. Now the symbol for frequency is nu, which is a Greek letter that kind of looks like a V. And frequency is the number of waves that pass a point in a given period of time. So if we look at let's look actually down here at the different wavelengths we have. If here is my point that I'm hitting, we can see that all of these types of waves are hitting or moving at the speed of light. And so if we have a large wavelength versus a small wavelength, my crests or my high intensity of amplitude are going to be hitting more frequently down with this low wavelength because I have more crests over a given period of time. Where up here with my large amplitude or my large wavelength, I'm going to not hit as often. So when I have a large wavelength, that means I'm going to have a lower frequency. I'm not hitting as often. But if I have a really small wavelength, right, lots of peaks showing up because they're just back to back, then I'm going to have a higher frequency. I'm just going to be hitting a point more often. And that gets to our total energy. So our energy of our wave is related to the height or the amplitude of our light because it's going to have a larger force, but also the frequency. The more often that that the wave is striking or that my crest is passing over a given point, the more force there is. So we already talked about the difference between wavelength and frequency, right? I mentioned it here. They're indirectly proportional, so as one goes up, the other one goes down, and they are both related via this equation. So the speed of light, which is 3.0 times 10 to the 8th meters per second, is equal to lambda, the wavelength, times nu, the frequency. And so when we have a large wavelength, that means that we're going to have a small frequency because they're both equaling to a constant. And if I have a small wavelength, then that means I'm going to have a larger frequency to make up for it. Now let's practice the equation we just learned. Calculate the wavelength in nanometers of red light emitted by a barcode scanner that has a frequency of 4.62 times 10 to the 14 inverse seconds. So notice we have frequency and we want to calculate the wavelength. So the equation we can use that goes between the two is the one we just learned. Speed of light equals lambda times nu. All right, so we are trying to find wavelength. So to get wavelength by itself, I'm going to divide by frequency. So I'm going to get lambda equals the speed of light, 3.0 times 10 to the 8th meters per second, divided by the frequency, which is 4.62 times 10 to the 14 inverse seconds, which is like that. I like to write it like that because then you can see how my seconds will end up canceling out, and I end up just with units of meters. Now, make sure you're careful here. When you're typing this in your calculator, you want to make sure this whole denominator is being divided. You don't just divide by 4.2. If you get a number that's like, let's say, 10 to the 22nd, then you know that you didn't divide by the 10 to the 14. So just an aside, what you can do in your calculator is type in 3.0, this big capital E, 8, divided by 4.62, big E to the 14. This E is going to keep the 10 to the 14 all with this number. So you shouldn't even need any kind of parentheses. So work on learning how to use your calculator in this way. It will help a lot. All right, so we calculate that and we get 6.49 times 10 to the negative 7 meters. Now, one extra step you're going to be doing a lot in this area because our colored light that we see with our eyeballs is in nanometers. So we're often going to be converting in and out of nanometers. So just remember that 1 meter is 10 to the 9 nanometers. I kind of remember 9 nano. It helps, right? So I have a lot of nanometers in 1 meter. So I can go down here. I have 1 meter is 10 to the 9 nanometers. And so we multiply by that number, and I get 649 nanometers is my light. Okay, I want you to try to go backwards in this problem. So pause here, try to work on this problem, and then in about 10 seconds, I'll have the answer up. All right, so in this problem, we have a laser dazzles the audience at a rock concert by emitting green light with a wavelength of 515 nanometers. So we know wavelength equals 515 nanometers. Calculate the frequency. So we're trying to calculate the frequency. So immediately you should say, oh, Tasha just told me I was going to go in and out of nanometers. So let's just immediately go out of nanometers and into meters. So I'm going to do what I did earlier, 10 to the 9 nanometers in 1 meter. So you get 5.15 times 10 to the negative 7 meters. Now we could use our equation. We have C equals lambda times nu. Now we're going to solve for nu. So I'm going to divide by lambda on both sides. And we get nu equals speed of light, 3.0 times 10 to the 8 meters per second, divided by our wavelength. And again, when you type this in your calculator, make sure you keep that whole denominator together in a parentheses or something. So now we can see that our meters are going to cancel out, and I'm left with just 1/seconds. So our final answer, now if you get something like 10 to the negative, or like 5.83 period, then you didn't do your math right on the denominator. So make sure you keep that parentheses. Should have got 5.83 times 10 to the 14th inverse seconds, or hertz. So now we can see right up here the electromagnetic spectrum. And I just want to note a few things. So we just see this tiny little section here that is visible light. On the long wavelength side of things, this is low energy, is radio waves. It also has low frequency. Remember, we said that energy and frequency were related, so things with higher frequency would have higher energy, and we see that here. As we go from low energy radio waves, we then get to microwaves. Within radio waves, we have AM, FM, TV, cell radio waves, and then we hit up microwaves. If you've ever left some food in the microwave that doesn't adjust and you don't stir it, you'll see areas of really hot where your crests are, and really areas of really cold where your the bottom of your wavelength is. And then we'll have, as we get higher in frequency, we get to infrared. Now, right next to infrared in our visible, you might guess it's red. So infrared is right next to red. This is like heat energy that you would feel, right? Infrared glasses, you can see body heat from that. Then you get to red, Uroi G vivid up to violet, and next to violet is ultraviolet. So we're getting high energy. And we know ultraviolet is a lot more energy, right? It's a little bit dangerous for us. UV radiation can be dangerous. That's why we wear sunscreen. Continuing to get up in energy, we get to X-rays. We know that they can be dangerous. We have to wear special protection when we get X-rays. And then even higher energy is gamma rays, and those are very dangerous because they're such high energy. So key thing we are noticing, low wave frequency equals long wavelength, and high frequency equals short wavelength. All right, another property of waves is interference, and you maybe have seen this when you go in the ocean. We have small waves, and when they start to interfere with each other, they create big waves. That is what this is. So we have two types, constructive and destructive. Now, constructive is where waves are going to add up. Well, either way, they're going to add up, but they'll add up in such a way that their crests are aligned such that they make bigger crests. Okay, so this is called in phase. And we'll see this later with electrons. Destructive interference is a way that waves interact, but they're out of phase. So they add up. When they add up, we have a crest aligning with a bottom, and so they kind of cancel each other out, and we don't get any light. So we have two different sources of light where they add up to having no light. All right, a quick practice problem where we're going to arrange these types of radiation in order of increasing wavelength, frequency, and energy. So we have visible light, X-rays, and microwaves. And to me, it's easier for me to do it in terms of energy and kind of work my way backwards because I know about this light, right? So if I think about all those different types of light, which is the most dangerous? To me, that tells me the most amount of energy. So to me, the most dangerous is going to be X-rays. So they're going to have the largest amount of energy. And then we know that if we look at our electromagnetic spectrum, we showed that microwaves were actually the lowest amount of energy. And we use them all the time, right, to heat up our food. And then visible light is right in the middle. All right, and we know that frequency aligns proportional to energy, so we're going to have the exact same answer for frequency. And then wavelength goes in reverse, so we're going to have X-ray has the shortest wavelength, and then visible, and then microwave has the longest one. And these can be like, a lot of microwaves that we have are going to have wavelengths of like a centimeter, or about like a centimeter or a few centimeters. Visibles, so this is like in the centimeter range. Visibles in the like hundreds of nanometers, and then X-rays are even smaller than a nanometer. So now that we talked about interference, one thing that we can notice is that waves also diffract. So diffraction is when we have some waves. So these are the crests, right? So if we think about it like that. We have our waves. When they encounter a barrier that has a little hole in it, that are our waves will actually start to bend. So diffraction is the bending of a traveling wave. Now, key thing that the barrier has to have, right, this barrier here has to have a slit through it that's about the same size as the wavelength of light. Now, this only works with waves. Now, if I was to shoot particles at the same slit, they'll just go through, or they'll hit the barrier. They're not going to bend around it. So that's a key difference between particles and waves with diffraction. Now, we're going down here now. When we take a barrier that has two slits, and these slits are separated by a distance comparable to the wavelength of our light, we're going to see an interference pattern. And it will be related to the wavelength of our light and the distance between the slits and all this. It's a lot of cool physics in here. But what you'll see, right, so we have our light source. We are shooting, it has a wavelength. Now each of these slits will have diffraction going through it, causing some constructive and destructive interference patterns. So here we'll see on our film, right, so we have a film that is light sensitive. We'll see areas where we have destructive interference and they're black spots, and we'll have areas with constructive interference and we'll have bright spots. And so we'll have a different distance and path length of the light. Will determine the constructive and destructive pattern that we'll see. So we're gonna keep this phenomenon in our back pockets, ready to keep in mind when we are now observing what electrons start to do. Another cool phenomenon that we see is the photoelectric effect. And this was done by Einstein, and he observed that when you shine a light on a piece of metal, then electrons can actually get produced from the surface and get emitted. And these electrons are called photoelectrons. They're just electrons, but they came from light, right? They were excited by light. So we have the surface of our metal. We shine some light at the surface, and then an electron gets kicked off. And then it can get detected by current. So what happened here, what we kind of expect is that if I adjust the frequency or the amplitude of the light, we should get more electrons, right? So if I have higher frequency, that's higher energy, I should get more electrons. And I'd also expect that if I shine a brighter light, that's more energy, I should get more electrons. Right, we saw those relationships earlier. But what actually happened was not the same. So I have red light here. Now red light is low energy, has a lower wavelength or higher wavelength. And then I shine green, so that's higher in energy, about mid-energy. And then I have blue, which has higher energy. So you do see, initially with low frequency here, no electrons get emitted. Then as you increase the frequency, so we're increasing a little bit more, that we get some electrons emitted. And then if I increase the frequency even more, I get the same number of electrons emitted, but they're coming off a lot faster. So what is going on here? Let's look at this other data from this table that we see. So here we have lower intensity light and higher intensity light, where we are adjusting the frequency of the light and then seeing how many electrons get ejected. So when I have low frequency of light, right, so low energy, nothing comes off. Then you hit this point right here for this metal, where now electrons kick off. Now, it didn't matter if I was at low intensity or high intensity of light, they still kick off. The only thing that changes is how many electrons came off. So higher intensity light was able to kick off more electrons than lower intensity light. But the frequency limit right there, that was minimum, the minimum amount of frequency required to kick off any electrons, no matter how strong the light was. So this minimum frequency is called the threshold frequency. And that's how much, the key frequency required to remove an electron from that metal surface. So this is a little bit different than what you would expect, because you would kind of expect from the classical theory is that, it's more linear. There's no minimum that you need. So then Einstein proposed that basically light was delivered in tiny little packets called quanta or photons. We're going to use photons. And that the energy of each photon was equal to a constant called Planck's constant times by the frequency that it has innately. So the energy of the photon is proportional to its frequency. So if we were to plug that in to our C equals lambda over times nu, then we could solve for nu and divide by lambda on both sides, and also do the energy equals h Planck's constant times the speed of light over the wavelength. So both of these equations are basically the same, and you're going to be using them. Now keep in mind Planck's constant is this tiny little number. Now it's long to write, but it's a really small number. 6.626 times 10 to the negative 34 joules times seconds. And so what you'll end up seeing a lot of times is that the energy of a photon of visible light is around 10 to the negative 19 joules. You'll see that often. So that's a really good check that if you're dealing with visible light, is your value close to that. When we see light coming from like a light bulb, we just see a constant amount of photons. We can't see the individual little photons coming out. It just looks like a blanket of light. But when we have a source of light, it could be a laser, a star, a light bulb, any kind of source of light, lots and lots of photons are being emitted, right? So here's our little photons coming out. And so in a lot of problems, we're going to want to calculate how many photons are being emitted. So what you'll want to do is take the energy of your source, right? So that could be, a 50-watt light bulb, or however many watts there are, or how many joules there are from your light bulb source, and divide it by the energy of one of the photons in the light. So this number is this denominator here, that is calculated based on the frequency of the light, or the wavelength if you want to use the other equation. The energy of the source is going to be given to you in the problem, or given to you in your light source that you have. And then your number of photons you're going to calculate is always going to be a number greater than 1, because it's a number of photons. You can't have a partial photon. The smallest number of photons you could have is like 0 or 1, but it's always going to be a number greater than 0. And just an FYI, when we're talking about watts, you maybe have heard of a watt when you're dealing with how many, the energy of your light bulb. This is a unit of power, and it's really just a joule per second. So if I have 50-watt light bulb, then that means that I have 50 joules per second coming out of that light bulb. So you can interchange joule per second and watts. And this is going to be really helpful later on when we start to calculate how many photons are being emitted from a source. Okay, so here's our first one. Calculate the energy of a photon that has a frequency of 5.0 times 10 to the positive 14 hertz, or inverse seconds. So we want to calculate energy, and we're given the frequency. So the equation that we can use, the energy of a photon equals Planck's constant times the frequency. So that will be 6.626 times 10 to the negative 34 joule times seconds times by 5.0 times 10 to the positive 14 inverse seconds. So here we can see that our seconds will cancel out. We're just left with joules. We multiply that together, you should get 3.3 times 10 to the negative 19 joules. Okay, so this must be in the visible light, or close to it. A nitrogen gas laser pulse with a wavelength 337 nanometers contains 3.83 millijoules of energy. How many photons does it contain? So this is one of those questions where we're going to do number of photons equals energy from our source divided by energy of the photon. Okay, so energy of our source, it tells us that there's 3.83 millijoules of energy. So that is energy of our source. Now we are going to need that to be in joules, so we could do 3.83 times millijoules, and then there are 1,000 millijoules in a joule, so we'll get 3.83 times 10 to the negative 3 joules. All right, now we need to find the energy of a photon. Now we are given here the wavelength in nanometers, so we're going to need to use the energy of our photon equals Planck's constant times speed of light over our wavelength. Now our wavelength is in nanometers, so let's get that out. 337 nanometers. 10 to the 9 nanometers is 1 meter. So we're going to get 3.37 times 10 to the negative 7 meters. So plugging on in, we have Planck's constant, 6.626 times 10 to the negative 34 joules times seconds times the speed of light, 3 times 10 to the 8 meters per second, divided by our wavelength, 3.37 times 10 to the negative 7 meters. So let's see what happens with our units. We're going to have seconds cancel out here, meters cancel out here, and now I'm just left with joules. So that's good, because that's what we have for our source of our energy above. So plug that on in. We get 5.8985 times 10 to the negative 19 joules. So we're going to take energy of our photon up here, divide by it. So let's do 5.8985 times 10 to the negative 19 joules. Make sure that whole bottom part is in parentheses, and we're going to calculate that. So our number of photons equals 6.49 times 10 to the 15 photons. All right. So see, it's a number larger than 1, so it is many photons. If it was 10 to the negative something, negative 15 or something like that, that would be a fraction of a photon, and that's not possible. So back to that threshold frequency, right? We saw that there was a minimum frequency, or that threshold frequency, that was required for an electron to be emitted. So if we take that threshold frequency and we find the energy of that, that's going to be the binding energy. So the binding energy is equal to the Planck's constant times the threshold frequency. I'll put T for threshold. So when we have a shorter wavelength, right, or higher frequency photon, then we're going to have extra energy, which means that that extra energy is going to get converted becomes kinetic energy, or speed, which really explains what was seen in the experiment, right? Below the threshold frequency, we don't have any electrons emitted. Around the threshold frequency, it's going to be a little bit, like there's a little bit of some speed off the electrons, and then even higher, these electrons are going off a lot faster. So to find the kinetic energy of those ejected electrons, we're going to need to find the difference, right? How much energy did we put in through photon? How much energy gets absorbed in helping to emit or eject the electron, and then how much energy is left over. So we take our energy of our photon minus the binding energy to remove the electron, and that's how much extra energy there is. So we have, let's say we have barium. Now barium's threshold or binding energy is 3.82 times 10 to the negative 19 joules. So let's find out how much energy is involved in each of these sources of light, and then how much kinetic energy is there. So starting with the first one, immediately I'm going to just convert all of these into meters. So we'll have 6.20 times 10 to the negative 7 meters, 5.20 times 10 to the negative 7 meters, and then 3.5 times 10 to the negative 7 meters. So if we find the energy of each of these sources of light, so 620, then we're going to do, that's the energy of our photon, right? So we're going to do hc over lambda. So we'll have 6.626 times 10 to the negative 34 joules times seconds times 3 times 10 to the 8 meters per second divided by our wavelength. So I'm actually just going to put wavelength here. Now you're going to use all of the wavelengths. When it is 620, energy of 620, let's actually just make this energy of our photon. So when the energy is 620, we get our total energy of our photon to be 3.21 times 10 to the negative 19 joules. So we can see that our binding energy is greater than that. So this light source, 620, is smaller. That is less than the binding energy of barium. So there's going to be no ejection here. Whoops. All right, now if we do the same thing for the energy at 520, then we'll plug in our 520 wavelength right here in meters, and we get 3.823 times 10 to the negative 19 joules. So that is a little bit bigger than that. So if we take the difference, so kinetic energy is going to be our photon energy, 3.823 times 10 to the negative 19 joules, minus our binding energy, 3.82 times 10 to the negative 19 joules. And so we get a really, really small number, which is about 0.003 times 10 to the negative 19 joules. I get that that's not like mathematically the best way to write that, but you get my point. So a really small number, right? So we just barely hit that energy level. Now let's see what happens when we do 350. So energy at 350 nanometers, we're going to take Planck's constant, and then we're going to multiply it by the speed of light, and then divide by 3.5 times 10 to the negative 7, and we get 5.679 times 10 to the negative 19 joules. So now to find that kinetic energy, we're going to do that number, minus our binding energy, 3.82 times 10 to the negative 19, and we get about 1.859 times 10 to the negative 19 joules. So we can see a lot more energy is available for kinetic energy. So these electrons are moving a lot faster than these electrons at that lower frequency. So considering that we have the kinetic energy of the electron is equal to the photon energy minus the binding energy, which of these, let's figure out what's true. So if the photon energy is less than the binding energy, what is true? If it's equal to the binding energy, what's true? And if it's greater than, what's true? We already saw this. If a photon doesn't have enough energy, then we're not going to inject. But if it's just barely at that energy, so then we're going to eject it, but it's not going to move, right? It's not going to be emitted with a lot of kinetic energy. But if our photon that we shine at the metal surface is a lot higher energy than our binding energy, then our kinetic energy is going to be greater than 0, so it's going to shoot off with a lot more speed. So another question very similar. A metal will eject when its surface is struck with yellow light. What will happen if it's struck with ultraviolet light? So we have to think about yellow versus ultraviolet. So Roy G. Bivet. So our binding energy is in the yellow. So if I was to hit it with red or orange, nothing would happen. Yellow is going to barely get me ejected, and anything above it will eject with high kinetic energy. Now, ultraviolet, you have to say, is it below red or above violet? Well, we know that ultraviolet is above violet, so if I hit it with UV, it's going to come off a lot faster. So it's not true that no electrons would be ejected. They will not be the same as yellow light, because it would have to be yellow light to be the same as yellow light. They would have to be higher kinetic energy. There we go. And lower kinetic energy doesn't make sense if the yellow is the threshold. So we've been talking about what happens when metals are absorbing some energy, but let's talk about what happens to atoms in general when they absorb light energy, or H nu. So when an atom absorbs some kind of energy, now that energy can be heat, it can be electrical energy, it could be light energy, but the extra energy, so when atoms absorb energy, then the energy is going to need to get released eventually. It can't keep that high energy state. So when it releases the energy that it had absorbed, it often gets released as light energy. So we see this as fireworks or neon lights. So with neon lights, right, if I look at this hydrogen lamp here, the way these work is you input electrical energy, and then it excites the hydrogen molecules in the light source. So what happens now is the light energy that gets emitted after it was released, you can put it through a slit to really isolate it, and then a prism. And the prism will actually show, once it separates based on its different wavelengths of light in that source, it will emit or show a pattern of wavelengths that is really unique to that specific atom or molecule. And this is called the emission spectrum or the atomic spectra. So this can actually be used to identify elements in a material. This is also how elements are determined from stars, right? We can't physically go up to stars and determine what it is, but we can use the light source and then the spectra from that light source to determine what types of atoms or molecules might be in the stars. As the molecules get more and more complex, or the atoms, and have more electrons in there, then these different patterns get more and more complex. And so it gets a little bit more complicated to identify when you get more complex elements or molecules, but it still can work, and it's pretty cool. So Niels Bohr developed a model that helped to kind of explain what's going on structurally in an atom, especially regarding energy. So the big thing from Bohr was that energy within an atom is quantized. So where the electrons are found are in specific positions. And so atoms could only have specific amounts of energy. So how does that look? That would look like, here's our nucleus in the center, and then electrons are only going to be found on these kind of like orbits, or these radius so far from the nucleus. And so when electrons are in the atom, they can only be found at these specific radius from the nucleus, and the energy of the electrons is proportional to the distance from the nucleus. So further away means higher energy, closer in means lower energy. And so when an electron, let's say it's in number 2 here, if I excite it by adding in some kind of energy, it can jump up to another orbital, or an orbit, another position. But it can't like go in the middle. So it's only going to be found in these specific positions. And then so let's say it jumps up from 2 to 4, then when it relaxes back down, it's going to, it can release some light. When it releases light, that is, it's basically releasing photons. So photons get emitted. So here we can see, hold on, let me just erase my little example here. If we look here, we can see, so if we go up from 4 down to 2, I am emitting a green light. So that energy jump is like in the middle. Here I have a further energy drop, and so I am going to have a higher energy light that gets emitted. And then if I drop from 3 to 2, that's a smaller energy difference, and so I'm going to have a lower energy light that gets emitted. So we're going to start to determine mathematically what's going on there soon. Another scientist just proposed that basically particles can act like waves. So what was noticed was, as you get smaller and smaller in mass, then your wave behavior becomes more significant. So with electrons, because they are so small, the wave behavior of them is significant. But even something like a car would have this type of wave behavior. But because it's such a large mass, then it's not going to show it to the naked eye, but it would still technically have a small wavelength. So this de Broglie relation is specifically for, not for light, but for particles. Okay, this is key. So if I was to ask you, what's the wavelength of a particle, you're going to want to use this equation. If I'm asking you what's the wavelength of light or energy, you're going to want to use C equals lambda times nu, equation that we've been using so far. So the wavelength of particles is equal to Planck's constant still, but now it's divided by the momentum, by both the mass and the velocity. So the smaller my mass, the bigger my wavelength is going to be. So let's practice using the de Broglie wavelength. We want to calculate the wavelength of an electron traveling with a speed of 2.65 times 10 to the 6 meters per second. So we're going to use wavelength equals Planck's constant divided by mass times velocity. Now keep in mind this is velocity, not frequency. So when we're using this, Planck's constant is 6.626 times 10 to the negative 34 joules times seconds. Now I'm going to break up a joule. You don't have to do this, but I just want to show you. A joule is a kilogram times meter squared per second squared. Right, so there's a joule times a second. So that's Planck's constant. Now I'm going to divide by the mass. Now the mass of an electron in kilograms, we could look up from chapter 1, is 9.11 times 10 to the negative 31 kilograms. And my velocity for this electron is 2.65 times 10 to the 6 meters per second. So for units, let's just cancel some. We have kilograms, we have 1 second cancel out here. I have 1 meter cancel out here, and then the other second canceled out here. So what we end up with is a meter. So plugging that in, I get 2.74 times 10 to the negative 10 meters. I really want to make sure you try that calculation to make sure that you are using your calculator correctly. So doing a similar one, we're going to calculate the wavelength of a baseball. It has a mass of 0.2 kilograms and a speed of 30 meters per second. So we're going to use the same equation here. So we're going to have 6.626 times 10 to the negative 34 joules times seconds divided by my mass, 0.2 kilograms, divided by my speed, 30 meters per second. So plugging that in, and you should get 1.10 times 10 to the negative 34 meters. So you can see significant difference here. Here we have about 0.2 nanometers, and here's like 10 to the negative 25 nanometers. So electrons moving fast have a lot more of a wave behavior than a baseball moving pretty slow. Okay, what is the velocity of an electron that has a de Broglie wavelength approximately that to a chemical bond, which is 1.2 times 10 to the negative 10? I want you to try this one on your own. Pause now and come back in about 10 seconds after you press play for the solution. Okay, so we have the same equation. The wavelength of this particle is equal to Planck's constant times m over m times v. Now I want to solve for velocity, so I'm going to multiply velocity by both sides and then divide by wavelength to both sides. So we end up getting velocity equals h over m times wavelength. So we'll plug in our Planck's constant, divide it by my mass of an electron. We already used that. 9.11 times 10 to the negative 31. And then kilograms. And then by the wavelength, 1.2 times 10 to the negative 10 meters. So now, once we plug that into the calculator, you should get that your velocity equals 6.1 times 10 to the 6 meters per second. So very fast. Now we're going to jump back to diffraction. So you remember when we have light that goes through two slits, we saw an interference pattern. So now when we do the same thing with electrons, so we're going to pass electrons through the slits, and if electrons acted like particles, then they should basically just give two bright spots where the particles were able to enter through. But what we actually see is that when we shoot electrons through these two slits, we get an interference pattern. And this is similar to what we see when we shine light through these two slits. So this is one indication that electrons act like light or waves and not like particles. So far we have seen how electrons can act both as a particle, having mass and acting like matter, but we've also seen it act more like a wave, and from an energy perspective, having wavelength and having frequency. And we saw that specifically on the last bit when it had an interference pattern. but the weird thing is that you cannot see both at the same time. So they are complementary, which means that the more you know about one of those perspectives, the less you know about the other. So that leads us into Heisenberg uncertainty principle, where x is position and v is velocity, in this case, not frequency. And what the Heisenberg uncertainty principle says is that the change in, or the uncertainty in position multiplied by the uncertainty in velocity is greater than a constant. That constant is the Planck's constant divided by 4 pi. So when we know about, so since this is a constant, this number is always going to be the lowest value you could get. You're never going to get anything smaller than that. Meaning that just like we had with wavelength times frequency always equals the speed of light. So if frequency is big, wavelength is small, or if frequency is small, wavelength is big. So same thing here. The more we know about the position, meaning the uncertainty is small, that means the uncertainty in the velocity grows, and vice versa. With classical physics, when we think about how a particle moves in space like a baseball, we can consider the various forces acting on it, its velocity, position, and whether we have gravity or wind and different types of friction, the forces to help us know how that particle is going to move in the future. And with classical physics and all particles, they follow determinacy, meaning that they have a definite, predictable future. So if I throw a baseball at a given angle with a given velocity, and then we have gravity acting on it, then we can predict exactly where it's going to fall. But with electrons, we can't, and that has to do with that Heisenberg uncertainty principle. We can't know both the position and velocity with exact precision, so we can't predict the path. So we can say it's indeterminate, which means it has an indefinite future. We can only predict the probability of where it's going to be at any given time and what its speed is going to be at any given time. So rather than knowing this in this classical trajectory here, knowing exactly where a particle is going to be, an electron, we know it's going to be somewhere in this range of blue, somewhere in that distribution. So Erwin Schrödinger solved this equation that helped us to find out the probability of knowing where an electron is at any given point of energy and basically any location in the atom. And this is the equation here. We take this function, the symbol here, which is all of the points that the electron could be at, and we apply this, basically this calculus to it. And what we get out is that wave function again multiplied by the energy that it could be at. If we take that function and we square it, this is going to represent an orbital, which is really, instead of an orbit where we exactly know, like when we think of a planet, we exactly know where the Earth or a different planet is going to orbit. The sun, we know the position, but an orbital is a probability distribution of where that electron is likely to be found. These calculations, the solution that comes out of this equation, show us the size, shape, and orientation of where the orbital is in space, with 3 different numbers. So you are going to learn those numbers. So the first 3 here come out of the wave function and the Schrödinger equation. First one is principal quantum number n. This tells us the energy level. And that's also related to the radius. So the bigger the number, the higher the energy, and the larger the radius. The angular momentum quantum number is L. It tells us what type of orbital. So basically the shape. what is it looking like. The magnetic quantum number, M sub L, is the position on the XYZ. So orientation on an axis, X, Y, and Z axis. And then the spin quantum number here is the orientation of the spin. And for that, there's just going to be two numbers. And so it's like, is it going clockwise or is it going counterclockwise? What's it going to be? All right, so starting with N, the energy level. This is really similar to what we saw earlier with Bohr's model. N can always be a value of 1 or larger, and it's always going to be a whole number integer. It determines the size, the overall size of that orbital, and therefore the energy. So when we have N equals 1, that's going to be the closest one and the lowest energy. As we get N equals 2, that means it's going to get into a higher energy, higher radius from the nucleus. So the larger value of N, the more energy, and the larger the orbital. Both of those are true. One thing we need to think about is that when we have some kind of attraction, which we're going to have with our electrons in our atom, or else they wouldn't stay in there. So if I have an electron here and I have the nucleus in the center, there is an attraction. And attractive forces are all negative. So if we think about our energy equals a constant times the charges divided by the radius, then when we have two charges of opposite sign, so a positive nucleus and a negative electron, then our energy is going to be negative. Once we reach to the point where an electron has left the atom, so it pops off, we have infinite radius, then our energy goes to 0. So in all cases where we have an electron hanging on and being attracted to a nucleus, our energy is negative. So we're really thinking about, like, when we're talking about the energy is negative or lowered, we're getting more and more negative. As N, notice here with this pattern of our transitions, we have N equals 1, then we jump up way big for N equals 2, then a smaller gap to N equals 3, and so on. So as N gets larger, the energy between the orbitals gets smaller. So they get closer together. And it's related to this energy here. So the energy at any given level is equal to negative 2.18 times 10 to the negative 18 joules times 1 over that energy level squared. So that principal quantum number squared. We're not going to use this equation, but we will use a form of it later. So we'll practice with it. The angular momentum quantum number L is the shape of the orbital. It goes from 0 to n minus 1. So for every principal quantum number that we have, we're going to have an allowed L values. So L will always, right, so my first energy level is n equals 1. So my only possible L value is 0. When we have n equals 2, my L values go from 0 up to n minus 1. So n minus 1 in this case would be 1. So this is my allowed values. So these are the shapes. So when L equals 0 here, this is called an s orbital. Basically, it's scientists give the numbers a letter to help us kind of think of it in a different way. S orbitals are spherically shaped, so they're just circles. When L equals 1, has a value of 1, this is a p orbital. And this kind of looks like two balloons being connected by their knots. When we have L equals 2, this is called the d orbital, and it looks like a 4-leaf clover again, so kind of like 4 balloons tied together by the knot. And then when we have L equals 3, this is called an f orbital, and they look they're more three-dimensional, like this guy here. Now the next type of quantum number is the magnetic quantum number. This is telling us how each orbital is oriented in space. So it tells us, again, the orientation. Is it in the x-axis, like this one? Is it in the y-axis? Is it in the z-axis? Is it on a plane? So they are going to go from negative L through 0 to positive L. So like I said, they include 0. We're basically going to count up how many digits we have in between negative L to positive L, and that will tell us the number of orbitals. So for example, if L equals 1, my m sub L is negative 1, 0, positive 1. So I can count 1, 2, 3 digits are there. So that means there are 3 orbitals. The last type of quantum number is the spin quantum number, and that is related to the angular momentum of the electron in the orbital. It tells us the orientation of the electron, not just the orbital, but of the electron within the orbital. All electron spins are the same magnitude, they just different orientation, so we change their sign. So when we have a spin up electron, that's like a clockwise one, we're going to call it plus 1/2. Or if it's negative, or if it's counterclockwise, it'll be negative 1/2. Yeah, so you can kind of see that here. The only difference between these two electrons is which way they are spinning. So we can take the first 3 quantum numbers, n, l, and m, and it will tell us a lot about how an orbital is positioned. So again, n will tell us what energy level it's in, how far away it is from the nucleus. L is going to tell us the shape. So L is the sublevel of our n. So for n equals 2, here we are, n equals 2, we have 2 possibilities for L. We have L equals 0 and L equals 1. So this means that for the energy level n equals 2, I have an s orbital available and I have a p orbital available. These are the only allowed orbitals for this energy level, because if I had L equals 2, well, remember the rules, L has to be less than or equal to n minus 1. So I can't have up to 2. So for our s orbital, here we have L equals 0. So when L equals 0, the only m sub L is 0, sorry. So we have 1 digit here, meaning that we have 1 orbital in this sublevel. For L equals 1, here we go, over here, our p orbital, we have m sub L values of negative 1, 0, and positive 1, meaning we have 3 p orbitals. So we have 3 orbitals with this sublevel. These are just general rules on how to count up how many sublevels there are within a level and how many orbitals within a sublevel. But I really don't think that it's super helpful to memorize these, but rather you can always get them if you're understanding how to find them more graphically, like we've been doing. So just to find out, by the way, number of sublevels within a level is n. Number of orbitals within a sublevel is 2L plus 1. And then the number of orbitals within a level is n squared. So we can see that if I have n equals 2, my number of sublevels is 2, 1, 2, right? L equals 0 and 1. My number of orbitals within that level, so if I have L equals 0, I have 2L plus 1, so it'd be 2 times 0 plus 1 is 1 orbital, or 2 times L, L equals 1. So 2 times L is 2 plus 1 is 3, boom. And then number of orbitals within our level, so I would take n squared and I get 1, 2, 3, 4. Anyway, that's all that means, but once again, you can see it out here this way. So let's practice. What are the quantum numbers and names for the orbitals of n equals 4 principal level? So let's do that. When n equals 4, and it wants to know how many orbitals exist. So let's draw it out. N equals 4. So if we want to calculate the possible L values, we know that L goes from n minus 1 to 0. So what we're going to do is n minus 1 here is 3. So L equals 3, L equals 2, L equals 1, L equals 0. Cool. Remember, L of 0 is S, L of 1 is P, L of 2 is D, and L of 3 is F. So those are our orbital names. Now to find out how many orbitals exist. So what we want to do is find the m sub L values for all of these levels. So remember that m sub L goes from negative L to positive L. So let's start with m sub L. For L is 0, that means our m sub L is 0. For L equals 1, my m sub L is going to be negative 1, 0, positive 1. For L equals 2, my m sub L is going to be negative 2, negative 1, 0, positive 1, positive 2. And m sub L, or L of 3 is, our m sub L will be negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. So we have here, we have the orbital names here. We have 4F, 4D, 4P, and 4S. And the number of total orbitals we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16 orbitals exist in n equals 4. All right, so now let's do 5D. What are the quantum numbers associated with 5D? So we know that out front, the 5 is for the principal quantum number, so n equals 5. Now D, we need to think about what L value represents a D orbital. So when L equals 0, that's S, L equals 1 is P, L equals 2 is D. So my L quantum number for this orbital is a 2 from right here. And then how many 5D orbitals exist? Well, we need to find the m sub L. So m sub L, when L equals 2, is negative 2, negative 1, 0, positive 1, positive 2. So 1, 2, 3, 4, 5. So 5 orbitals exist in this sublevel. Now in this question, it wants you to know, we have a set of quantum numbers, and one of the sets has an error. And then down here, in this next question, we have sets of quantum numbers, and each of them have an issue. So I want you to pause, look at each of these. This first one, you're just picking which one of these has an error, and in this bottom one, you're finding the error and replacing it with something that would be allowed. So I want you to pause and try to figure each of these out, and then in 10 seconds you will be able to see the answer. All right, so you might have noticed that for this first question, we have n equals 4. That's all right. N just needs to be 1 or larger. L can go up to n minus 1. So for this one, we can have 0, 1, 2, or 3. For this L equals 1, that means it's a p orbital. For p orbitals, my magnetic quantum number can go from negative L to positive L. So for L equals 1, I could just go negative 1, 0, positive 1, meaning negative 2 is not allowed. So to correct it, it would just need to be somewhere within that range. Here for these bottom sets, sorry about the bottom being a repeat, but for A, when we have n equals 3, the only L's we can go up to is up to 2. So in this case, that one will not work. So you could either change L to be larger, to be 4 or higher, or change our L to be only up to n minus 1. So I would change L to be equal to 2. So my m sub L would work. For this next, for B, we have n equals 2, meaning I can have L of 0 or 1, so that checks out. So m sub L can go from -1 to +1, meaning that that one won't check out. So I would have m sub L be -1 or 0 or +1. For C, we have n equals 1, so the highest L we can have is 0. So L needs to equal 0 in this case, or I need my n to be larger for that to work out. So now we get to finally talk about how this model helps us predict or explain how the atomic spectra works out. So remember, we saw when we excited an element, we would get a distinct wavelength of light that would appear when we put it through a prism and was able to detect it. So what happens is when an electron is excited, right, we add energy into it, it goes from a lower energy up to a higher energy. So we can see here we go from n equals 1 up to n equals 2. We excited that electron. Now this could be excited through electrical signal, right? We could add electricity, we could add heat, we could add light technically, but we could have to add it to the correct amount of energy for it to jump up to that level, right? If we added less, it wouldn't quite get up to the next level and it wouldn't work out. Then, after that electron is up at this higher energy level, it's going to relax. Now, it could relax down all the way back down, or it can just relax to an energy level below it. It doesn't have to be all the way back. And it's going to relax because these high energy levels are unstable. It's not going to be able to last up there long. When it relaxes, it shoots off a photon. So a specific frequency of light gets emitted. And this represents, this wavelength that gets emitted will correlate to the energy between the levels. So we can actually calculate that frequency or wavelength of light. So what we get to do is look at the wavelength of light that it gets emitted from our, in this case, hydrogen atom, and calculate the difference in energy levels between two different states. So if I have n energy levels, then I'm going to be able to have n minus 1 transitions and therefore n minus 1 lines that I would be able to detect after it's been excited. So we take our wavelength and we can determine the spacing, the energy spacing between the energy levels that the electron relaxed down to. Because the energy of the photon that's released is equal to the difference in energy levels between them. So the equation, we're going to have the final state of the electron minus the initial state is our change in energy of our electron. So this change in energy of the electron is equal to negative 2.18 times 10 to the negative 18 joules divided by, or times by, 1 minus the final principal quantum number squared minus 1 over the initial quantum number squared. This works both ways, either the amount of energy that if it started low and went high, right, then my final would be up here, or if I relax down. So we could use this equation either way. So let's think about this. We want to determine the wavelength of light that gets emitted when an electron makes the transition from n equals 6 to n equals 5. So here we have n equals 6 is my initial, and it drops down to n equals, and f, or final, is equal to 5. So we have an electron emitting, or electron dropping in energy, meaning a photon gets emitted. So let's find out that change in energy of my electron. That's going to equal negative 2.18 times 10 to the negative 18 joules times 1 over the final squared. So final is 5 squared minus my initial state was 6, so 6 squared. I could plug that into the calculator, and what I get is a negative 2.6644 times 10 to the negative 20 joules. So my electron lost that much energy. But we know that energy just can't be lost, it's transferred. So this is the amount of energy that gets transferred to my photon. So my atom or my electron lost that much energy, meaning my energy from my photon is going to be negative of what the change in energy of my electron. So that means my photon energy that it gained was positive 2.6644 times 10 to the negative 20 joules. So now that I know how much energy my photon has, I can use my photon energy equation. E equals hc over lambda. Since I'm trying to solve for the wavelength, I can put it right in there. Now notice I'm trying to solve for lambda. And I have the energy of my photon. So what I get to do is a really nice trick. I get to both multiply up the lambda at the same time that I divide back down the energy. This changes my equation to be the wavelength equals hc over my energy. So I could do 6.626 times 10 to the negative 34 joules times seconds for Planck's constant, times by 3 times 10 to the 8th meters per second for the speed of light, divided by 2.6644 times 10 to the negative 20th joules. And notice my joules cancel, my seconds cancel, I'm left with meters. Plug that in the calculator and I get 7.46 times 10 to the negative 6 meters. So if we want to get this in nanometers, which when we think about light, oftentimes we're thinking about it in nanometers, I can multiply this by 10 to the 9 nanometers equals 1 meter. So I end up getting 7,460 nanometers. So key thing here is when I have an emission, right, my electron drops in energy, then I take that energy and I convert it into a photon energy. So I need to change the sign to find out my energy of my photon. Okay, let's find out. Determine the wavelength of light absorbed when an electron in a hydrogen atom makes a transition from n equals 2 to n equals 5. So now basically what we have is we have an electron, is n equals 2, there's my initial, and we excite it. We add energy through light, so boop, we added light in, and it jumps up to my final energy level of 7. So now instead of I'm converting, my electron is losing energy, and it gets converted into light, my light is actually it's exciting it. So let's see what happens. All right, again, we're finding the wavelength. So let's find out the energy associated with my electron here. So I'm going to use my equation, negative 2.18 times 10 to the negative 18 joules times 1 over my final, which in this case is 7 squared, minus 1 over my initial, which is 2 squared. When we do that, my change in my energy of my electron equals 5.01 times 10 to the negative 19 joules. Notice it's a positive number, right? Because my electron gained energy. So in this case, we are able to just say how much light energy was able to be transferred. So here for an excitation, the energy of my photon is transferred exactly over so it will be the positive of my change of energy of electron. So I get to do energy of my photon equals hc over lambda. So once again, we can solve for lambda equals hc over my energy of my photon. So I get 6.626 times 10 to the negative 34 joules times seconds times the speed of light. That is to the 8th, sorry about that, divided by my energy, 5.01 times 10 to the negative 19 joules. So my wavelength here that I need to shine on to my atom is 3.97 times 10 to the negative 7 meters. So if I multiply it to get nanometers, then I get 397 nanometers. So this is a type of blue light, so high energy light. If I shine this exact frequency or wavelength at my atom here, then it will be able to excite it up to this energy level. So let's go back to those wave functions for a bit and the probability density. If you remember, if you take that function and you square it, it tells us the likelihood of finding an electron in a given point of space. So here for the 1s orbital, we see that it has that spherical shape, meaning we're likely to find our electron in there. The further we go away, the more it's going to decrease. So we're not going to be able to find it further away for this n equals 1s orbital. You'll also find there are these nodes, and that's where the function is going to drop to 0. So here we don't have a node, but if we go to the next slide, the further away we get from the nucleus, so when n gets larger and larger, greater than 1, then we're going to get some nodes. So that will be areas where we won't find the electron. The probability of finding it would be 0. It's unlikely to find it there. So here we can see when n equals 2, so for an s orbital, here's our node, or where the probability density drops to 0, and that's where we would have a difference between my n equals 1 and my n equals 2 orbitals. And for n equals 3 here, we have 2 nodes, a node in between our n equals 1 and n equals 2, and a node between n equals 2 and n equals 3. We can take these different plots and these probabilities to also determine the distance or the likely distance of finding our orbital or electron in a given orbital. So here we can see for an s orbital, the 1s orbital, we can the maximum or the highest likelihood of finding an electron is at 52.9 picometers, and so that's kind of where we consider like that orbital distance from the nucleus. So looking at L equals 1, this is the s orbital. When we look at it, we just have a single little bell here. There's no nodes. This is indicating that it is more of a spherical shape. This is the lowest energy orbital for our principal energy levels. The number of nodes is always going to be equal to n minus 1 for our s orbital. So if I have a 2s orbital, then my number of nodes would be n minus 1, which would be 2 minus 1, or 1. So for a 2s orbital, it would look like, if we go back a slide, you'd see that there is one node that was there, right? So we'd have a 0 here, and it would jump up like that, right? And so there's our node for n equals 2. For L equals 1, these are p orbitals. We know that when we solve for m sub L, we have 1, 2, 3 digits for our p orbitals, meaning that there are 3 of them that exist. And this correlates to the 3, pointing along 3 different axes, either the x-axis here, the y-axis, or the z-axis. And this is the next lowest energy orbital. And it has 2 lobes, one node at the nucleus, right? So since there's a node at the nucleus, then we will have 2 lobes here. For L equals 2, this is our d orbital, When we solve m sub l for d orbitals, we have 1, 2, 3, 4, 5, and this correlates to the 5 d orbitals that exist. And these are actually, instead of being directly on an axis, these are on a plane, since they're in 2 dimensions. So we have one on the xz, one on the yz, one on the xy axis, and then we have one on the in-between axis, and then this really funky one with a kind of looks like a p orbital with a little lobe. But most of them are this 4-lobed shape, or kind of think of it like a 4-leaf clover, and then just this one kind of strange one. And since these are higher than the p orbitals in energy level, so they have more nodes as well, where electrons would not exist. For L equals 3, this is our f orbitals. With f orbitals, we have, this should be L equals 3, we have go from -3, -2, -1, 0, positive 1, 2, and 3. So we have 7 f orbitals that exist. These are 8-lobed mostly. There are a couple that are more strange, but we can see that these are in 3 dimensions. So there's more energy there and more nodes. But these are the 7. You do not need to be able to draw these, but just kind of recognize that the more complex they are, the higher in energy they are. So to focus on some concepts, I want you to read each of these problems, and then I'm going to pause here, and I want you to come back. I want you to also pause, come back in about 10 seconds to see if you got it, if you're on the right track. All right, so if we look at this first one, it says an atom's 2p orbitals have what in common? We know that all the 2p orbitals have the same shape. They all have the same energy level and the same L, right? Because they're all p's, but they're all going to differ in their orientation or where they take up space. For our quantum numbers 2, 1, and -1, what does this describe? Well, we know that L, this second number here tells us the shape. And S is L equals 0, and P is L equals 1, so this is a p orbital. Here we also have a p orbital, it's just in a higher energy level, so this is also p. And here when L equals 0, this is an s orbital. And if an orbital has L equals 3, could it exist in an n equals 3 shell? No, the first one it could exist in is n equals 4. As we talked about earlier, these orbitals are, and how we think of them, are determined from some mathematical wave functions that involve much more chemistry and math and physics. But because of this, they are a function, and they actually have positive and negative values. And these nodes that we've been talking about indicates where the function hits 0, but the in-between is where our signs are going to change from positive to negative. So the sign of the wave function is also called the phase. And this will become way more relevant later on when we talk more about bonding and when you do organic chemistry in the future. But when we can say that when they interact in phase, that they have the same sign. And when they're out of phase, they have opposite signs. This is very similar to when we had when we saw our diffraction pattern or interference pattern. So if I have a 1s orbital, there's no lobe here, so it would just have a single phase. We would just call it like positive. But if I had a p orbital, we could consider it like this, where we had a positive and a negative side, then mathematically it would look like we had a positive, a 0, and a negative side. So our orbitals also technically have signs. So for our challenge problem, we're going to do this example where we have, it's possible to determine the ionization energy for a hydrogen atom using the Bohr equation. Calculate the ionization energy in kilojoules per mole of a hydrogen atom, making the assumption that the ionization is from n equals 1 to n equals infinity. So there's our final and our initial. So we're trying to find out how much energy it takes to go from our lowest level up till it escapes and n equals infinity. So what we're going to do is the energy of our electron is going to be equal to, right, negative 2.18 times 10 to the negative 18 joules times 1 over my final, that will be infinity, weird, squared, minus 1 over my initial, 1 squared. Now 1 over infinity, we can basically make that be equal to 0 because 1 over a giant number is 0, it approaches 0. This is a little bit of calculus. And then minus 1 over 1 is 1. So what we get here is positive 2.18 times 10 to the negative 18 joules. So this is how many joules per atom or electron in our atom. So what I get to do now is just a bunch of conversions to get 2 kilojoules per mole. So we get to convert our joules to 1,000 joules is in a kilojoule. And atoms, to get to moles, we're going to use Avogadro's number. So I'm going to put atoms up top, 1 mole on bottom, and I get to use Avogadro's number here. And what I get is 1312 kilojoules per mole. So this is an approximation we could use on how much energy it takes to excite an electron from its most lowest energy level up to infinity.